So National Electric Code requires oversizing for protection in the event that there is a short circuit. For protection in the event that the system's not running and it's going up to its maximum voltage, that the electronics and cables can still be rated for that maximum voltage and then some. And so throughout National Electric Code, the very common rule of thumb, when you don't know how to oversize something for National Electric Code, oversizing by 25% often does not steer you wrong. If there are special exceptions, generally it's getting rid of the oversizing protection requirement because there's excessive use of overcurrent protection already. And that might allow for a downsizing or an elimination of certain parameters. But the standard parameter is, take your short circuit current, add 25% to it, and that's what the current capacity of the conductor needs to be rated for. And as we saw in our National Electric Code class, there are additional provisions like how many conductors are in a confined space, whether it be a conduit or adjacent to a rooftop. That might say there's more heat in the environment than normal, and so we have to derate because of heat on top of that. So why might solar be different? Why would solar have additional voltage and amperage oversizing requirements beyond the standard 25%? Solar, its voltage and amperage ratings are given at a test condition that is not reflective of their field performance. That 60 degree Fahrenheit to 77 degree rooftop temperature day is not reflective of the system on a sunny winter day when it's 15 degrees outside, not 60. Or a hot summer day when it's 160 degrees up on the rooftop instead of 77 degrees in the laboratory environment. National Electric Code will say, absent anything else, absent the use of module level panel electronics that are basically overcurrent regulators that you're already putting in line. If you're doing all this other stuff, then you use the standard oversize of 25%. But if you're just putting a dumb solar array without module level panel electronics up on the rooftop, without any kind of voltage regulating device coming out of the panels themselves, that circuit then has to be sized not just for our typical 25% oversizing, but we're going to make you add an additional 25% because you're taking the open circuit current or open circuit voltage, the short circuit current at standard test condition and using that for your calculation. And what we need you to do is allow for the normal oversize that you normally would do, and then recognize that because voltage and amperage on the system fluctuates so greatly in the field versus what you get at standard test condition, absent any other engineered calculation or current regulating device, we're going to make you do an additional 25% for the solar conductors between the array and the home run. And so NEC might not require an additional 25% oversize on top of its standard 25% oversize if you're using module level panel electronics, but it would if you're not using module level panel electronics. Again, that's not usually a very big deal because with solar conductors that are very long, you're often oversizing anyway to accommodate for voltage drop. But it can be confusing because you'll end up with large circuits that can carry 30, 35 amps, and it's only a 8 amp circuit. So that to an electrician that can be, well, why is this so oversized? you're oversizing it by 25% times 25% for the typical NEC oversizing rule of thumb for your solar circuits only, not between the inverter and the service panel. Between the inverter and the service panel, you already have overcurrent protection, the breaker on the service panel, plus the fact that the inverter is limiting the output of the system. We're talking about the raw power lines between the solar array and the inverter that need not just the typical 25%, but an additional 25% on top of that to account for the fact that there's more variables in a solar circuit in terms of environmental conditions than there is in a typical circuit in a building. And there are certain effects that can boost the production of a solar array momentarily. Just how the sunlight wraps around the edges of clouds can cause a fluctuation in performance. High altitude is another one to be careful for when you're using your sizing calculations. Even the PV Watts weather station selection, if you're up in a mountainous region, you want to make sure your data set is coming from a high point of elevation, because the Earth's atmosphere, it does play an impact. Just the difference between high noon when the sun is directly overhead, that photon from the sun to hit your service panel, it travels through less atmosphere than at 10:30 a.m. when the sun's at an angle. That photon travels through more atmosphere. And then in the early morning or early evening, the atmosphere thickness is even greater, even longer length, to the point where the sun can still be up at the tail end of the day, but that atmosphere thickness is so long that it diffuses the light to the point where it doesn't turn on the solar array by the time it hits. And so out of all these items, we've already talked about temperature, we've already talked about altitude. You don't need to worry too much about the edge of the clouds increasing performance, but know that it can happen. Albedo is the reflection of sunlight off of surfaces. To reflect sunlight off the bottom of a white roof back onto the bottom side of a bifacial solar panel, yes, that does increase performance, but we're talking about maybe a 10% increase in performance. Best case scenario, 20%. And I mean, that's for double axis trackers on top of a field of snow. There have been manufacturers looking into reflective systems for reflecting more light onto solar, and that gets into some inventions being a little bit too theoretical and not pragmatic. Also, manufacturers don't want you to increase concentrations of sunlight onto their solar cells. The temperature from that can cause the module to be out of spec. So, in general, it's nice to acknowledge that yes, you can reflect sunlight off of a surface to get more production out of the arrays, but also that is a very unusual practice, which when done intentionally could even result in voiding the warranty of the product. Air mass thickness, the reason why that's important is because standard test condition is done at an air mass thickness of 1030, where the air mass is a 1.5, whereas at high noon, the air mass is a 1. And so the photon, at 1030 is traveling through 50% more diffusion caused by atmosphere thickness than at high noon, and that plays a impact. And so I guess the quiz question over air mass thickness would be, if The sun is up at 10:30 at a 77-degree rooftop temperature with 1,000 watts per meter squared in the sunlight versus high noon at the same rooftop temperature at the same amount of sunlight, which produces more? And the answer is high noon because there's less air mass. Does solar down in the valley versus up at the mountaintop, no shade either case, which produces more power? Up at the mountaintop would because of less air mass thickness.